Welcome viewers. In this video we are going to do design of Substation Gantry Foundation Eurocode. This is stage 7 out of 7, which is a final stage. In this we are going to do design of pedestal or column. These are the various stages in a design of Substation Gantry Foundation using Eurocode. Number 1 we have seen already is overview of calculation. Second one is foundation and soil parameter loads and load combinations. Third and fourth are stability check and anchor bolt design. Fifth one is a design of bottom slab, and sixth one we have seen already the punching and one-way shear. Now this is stage 7. In this we are going to do design of pedestal. Now let we look into that Excel calculation. So on the screen you can see that Excel sheet which we have calculated for the design of gantry foundation. So this is a section which we are going to discuss about the design of column. So first thing is we need the input like a column dimension and loads. So for the column dimension we already assumed the column size as 600 mm in the previous video. That foundation and soil parameter, that is in the stage 2 we have fixed these sizes. We can say that we have assumed these sizes. So least lateral dimensions means it is 600 mm, that is in plan view of the column, and the clear height of pedestal or column is capital D minus small t plus small d. So this means you can see on that foundation and soil parameter which we have assumed earlier. So the d is nothing but the depth of foundation which is below the ground level. So it means 2.5 meter. In that we need to deduct the bottom pad thickness 400 mm. So 2.1 meter. In that we need to add the plinth level. It means from the ground level to the top of the column or pedestal. So totally it is 2.4 meter. So that is what considered here. Next one is the maximum compression per pedestal, maximum tension per pedestal. So these two input we need to consider from the table which is listed here. So for this we need to consider the ultimate limit state load combinations for with and without deviation, conducted deviations. So this load combination and load calculation we already discussed in the stage 2 video. So from that this tension and compression, maximum tension and compression per pedestal need to extract. Next one is the self weight of the pedestal or column. So this we need to calculate like simple that size of the pedestal, that B into L, it means 600 by 600 mm, into the clear height of the pedestal which we have calculated here as a 2.4 meter, into the density or specific weight of the concrete GC. So here we need to consider the dry density of the concrete. So those are we already assumed in the stage 2 video. We have assumed as 25 kilonewton per meter cube concrete weight, unit weight. And the next one is that the total vertical downward load is nothing but the CP plus VP. So the CP is a compression load which is from the structure, and VP is the weight of the pedestal or column. So adding these two we are getting 594, and the total upward load, you can call it this as a net vertical upward load. So net vertical upward load means we need to subtract the self weight to the tension which is coming from the structure. So TP minus VP. So this will give you the net vertical upward load or tension for pedestal. Next one is maximum shear force at the pedestal top. So this we already having these values here. So these are the values for ULS load combinations. We have discussed this in stage 2 video. So this is a total shear force which is going to act on the entire foundation, which is comprises of 4 pedestal. So for single pedestal, we just need to divide those into the number of pedestals for the foundation. So we have considered in the stage 2 video 4 number of pedestal. So this loads to be divided by 4 instead of getting the per column loads shear force. So both the ways we need to find out those. Next one is moment at column base. It means we need to calculate the moment where this total height of the column is meet. So the column and bottom raft meeting at this point. So we need to find out the moment at this area which is caused by the horizontal force. So these are the two horizontal force which is applied in the top of pedestal from the structure. So the structure is going to mount here. So we are having the horizontal forces only in the top, and we need to find out what is a bottom force which is causing the bending moment due to this horizontal force. So for that we need to consider this height as a lever arm distance, this clear height of the column. So we already know the clear height of the column is 2.4 meter. So this we need to multiply it with these horizontal forces. So this will be called as MUY and this is MUX. Sorry, this is MUX and MUY, but only that for MUX it should be that a clear height should be multiplied with the HUY, and MUY HOX to be multiplied with the clear height. So now the column dimension and the loads are clear. Next we need to check for column slenderness. For check for column slenderness, first we need to do this basic calculation. The moment of inertia, we all know that it is BDQ by 12 is the equation to find the moment of inertia. So applying that 0.6 into 0.6 cube divided by 12 as a column size, we are getting 0.11 meter power 4, and plan area is a B into L, 0.6 into 0.6 equal to 0.36 meter square. Radius of gyration, we all know that it is equation is square root of moment of inertia divided by cross sectional area. So then applying this, it is coming 0.173 meter. And next we need to calculate the effective column height. So this is mentioned in figure 5.7 of EN 1992. So you can see the right hand side, you can see that PDF file of EN 1992 part 1 section 1. So in order to get the figure 5.7, we need to refer page number 68. So here you can see the picture 5.7. So that shape is shape of the length of the column is showing here. So as we know that our foundation is like that, which is a cantilever, because here you can see on the top it is a free end and there's a bottom which is connected to the bottom pad. It means the fixed end. So in the picture in the right hand side, the second B case is matching to us. So we need to consider 2 times the clear length. So that is what considered here. So 2 into 2.4 is a clear distance which we are already calculated here. It is 4.8 meter. It's a effective column height now. Next one is a slenderness ratio we need to consider. The slenderness ratio is nothing but effective column height LO divided by radius of gyration. So radius of gyration we already calculated. So this is also explained in class 5.8.32 in the same page 68. So here you can see the slenderness ratio is defined as lambda equal to L naught divided by I. L naught is the effective length which is described in the 5.8.3.2 to 7. So this here it is described, and I is a radius of gyration. So these are mentioned here in the class 5.8. 3.2. So the same way we have calculated that. Next one is design value of concrete compressive strength we need to find out. For that equation is 0.85 into FCK divided by gamma C. So gamma C, which we already seen in the first stage of video, which is a partial safety factor for material concrete. So which we have considered as 1.5 meter as per table 2.2 EN 1992-1. So FCK, we know that it is a concrete characteristic compressive strength. So that we have already discussed in design of bottom slab, which is in stage 5. So here you can see that FCK, compressive strength of concrete, is 30 megapascal. So 0.85. So this equation we can find out in class 11.35. So for that page 190 to be referred in EN 1992 part 1 section 1. So here you can see the page number 190 states that FCD, that is compressive design compressive or tensile strength, equal to alpha CC into FCK divided by gamma C. So that alpha C here it may be vary according to the national annexure. The recommended value is 0.85, which is stated here in the notes. So we are considering this equation as 0.85 FCK divided by gamma C. So for that the design value of compressive strength is coming as 17 megapascal. Next one is we need to find out the relative axial forces. So this is as per class 5.8.3.1 page 67. So if you go to the page number 67, so here is the equation for relative axial force N. So you can see here N equal to NED divided by AC FCD. So AC, we already know that it is a plan area of column, and FCD we just calculated as 17 megapascal, and PU equal to NED. So PU we already calculated as a compressive strength here, total vertical downward loads, which is a summation of compression load from the structure and addition to that self height of the pedestal. So we are applying these values into this equation. We are getting 0.098 as a relative axial force, which is stated in class 5.8.31. And the next one is we need to find out the limiting slenderness ratio. So the limiting slenderness ratio also given here as lambda limit equal to 20 into ABC divided by square root of n. So we already calculated the n value. And what is ABC? So ABC definition is given here. A equal to 1 divided by 1 plus 0.25 EF. So if 5 EF is not known, even the 5 EF definition also given, it is a creep ratio. So this calculation will lengthy if we are going to work out all the small values in order to find out those. But in order to shorten this, we can consider the direct value A equal to 0.7 and B equal to 1.1, C equal to 0.7. So this value we can directly apply. So if we are going to apply this here, so 20 into 0.7 into 1.1 multiplied by 0.7, we will be getting 10.78. So that is what we have considered direct value as 78. So now we have find out the limiting slenderness ratio as 34, which is greater than the actual slenderness. So hence we can call it as the column is safe for slenderness. Next one is we need to check column reinforcement requirement or type, how to do that. And for that we need to refer class 9.5.1 and note 1 of EN 1992 part 1 section 1. For that page number 164 to be referred. So in the right hand side you can see that PDF file. So here it is mentioned that this class deals with the column for which the larger dimensions h is not greater than 4 times the smaller dimensions. It means for longitudinal reinforcement, which is mentioned here in a 9.5.2 class, we need to do as a minimum reinforcement. A is minimum. This equation we need to apply in order to find out the reinforcement. But if it is exceeding the 4, let we check into our calculation. So it means that 4, it should not be greater than the 4. But here what it is happening is a ratio of effective height to the least lateral dimension. We are getting 8 because 4.8 meter is our effective column height, that divided by 0.6 meter, that is least lateral dimension, is having 8 as a number, which is greater than the 4. So then this column to be designed for bending, compression, tension, and combined with the bending. So likewise we need to decide. Suppose it is 4 or less than 4, then the column satisfy nominal reinforcement as per class 9.5.2 in notes 2. So the notes 2 is very simple. So we can directly apply this vertical compression loads NED multiplied with 0.1 and divided by FYD. Then we will get the reinforcement requirement for that. But our case the value is 8, which is greater than 4. Hence we need to do the compression combined with bending and the tension combined with bending. So those some little bit tedious work we need to do in order to calculate the reinforcement. So coming to that detailed calculation of longitudinal reinforcement, first we need to find out the effective cover. Effective cover is nothing but we need to uh, reduce the clear cover with the diameter, half of the diameter. So that 50 mm we can assume as a clear cover, that minus that detecting the, sorry, it should be added with half of the diameter should be added here. So it is a 60. So why it is coming as a 60 is we have assumed the diameter of the main reinforcement here is 20 mm. So that 50 plus 10, it is a 60 mm. Now the size, cross sectional size, we know it is 600 mm. So that 60 divided by 600 mm we are getting 0.1, that is D2, effective cover divided by the column size. So this is required in order to find the reinforcement from the chart. Next one is we need to find out the total factor moment. So the total factor moment, we are going to add these two values, which we already calculated. Moment at column base is 31.88 kN in MUX and MUY is 33.61. So adding these two, 65.484 kN meter we are getting. So now we need to apply this equation. So this this equation is where it is going to arrive is for tension combined with bending and compression combined with bending. We are having some charts to be referred, because this EN 1992 part 1 section 1 will not have the details about the longitudinal reinforcement of column design. According to that national annexure and the local national level books to be referred for designing this column reinforcement. So there are two charts you can see on that Excel tab, not to be delete, which is mentioned in the name like that. So the first column means it is applicable for compression and bending. The second one is applicable for the tension and bending. So these values are extracted and made it in a tabular form in order to do some auto calculation based upon the mu by bd square fck and n divided by bh fck. This applying this equation we will be getting some value. Based upon that and the factor, base factor m by fck, m by bd square by fck, so those equations are displayed here. Accordingly this interpolation method is applied and the values to be extracted from this table. So we need to find out this requirement mu by bl square into fck. So we know that moment is 65.484 and b and l are 600 mm, and fck we know that it is a 30 megapascal, which is already seen in 5th stage of video, and we are getting 0.02. Similar like pu by bl fck we need to apply. So this also we all note that pu is nothing but the vertical compression force, which already we have calculated here, total vertical downward loads, and from this we need to find out the correction factor depending on axial load. So for this we need to refer class 5.8.3 notes 3 of EN 1992 part 1 section 1. So page 75 to be referred in the right hand side PDF file. So here you can see, in order to find out the curvature or correction factor, the equations are given here. So in the node 3 Kr expression is given. So Kr equal to Nu minus N divided by Nu minus N balance, which should be less than or equal to 1. So the definition for N also given here. N we already calculated as relative axial force, which is calculated here in order to check the slenderness value. And NED we know that it is axial force downward and upward, we have calculated already here, NED and NEDT. So corresponding to the case we need to apply. So this is compression with bending, so only NED we need to consider, that is total vertical downward loads, and Nu is 1 divided by mu, and N val is value N at equation. So the value is directly, it is given as 0.4, we can consider the same, and this mu, or I think it is omega value. So this is given as AS into FID divided by AC into FCD. So AS is a reinforcement total area, we need to calculate those, and AS is the area of concrete. So we are going to apply here those equations. So omega value, if we are going to calculate, is AS actual into FID into AC. So this value is FCD. So that actual reinforcement which we have calculated by assuming 4 numbers of 20 mm dia and 8 numbers of 20 mm dia. So total number of reinforcements. So these 4 numbers is at corners and 8 numbers is intermediate. So totally 12 numbers of 20 mm diameter we assumed that. In that it is actual reinforcement is 3769. So based upon that we are multiplying with FID, we already discussed in stage 5, which is a design yield strength of reinforcement 437 megapascal, divided by AC, we already know that it is a plan area of the column 0.36 meter square, that multiplied with the FCD is a design value of compression in concrete. So apply that, we are getting 0.26 as a mu value, omega value. And the next one is Nu equal to 1 plus mu, it is 1.26, and N val is 0.4, that we are considering directly, and hence correlation factor. So we are having all the inputs for the correlation factor equation. Nu is 1.26 and N is a relative axial forces which is 0.098. We already calculated that. So we are getting correlation factor is equal to 1 because this correlation factor is more than 1, so it is considering a minimum of this equation and the 1. So the correlation factor is 1. Suppose actual correlation factor is 1.35, but this equation stated that the correlation factor should not, the correction factor should not greater than 1. So we are considering this as 1. Now we need to refer the column design chart. So this value AS FYK BH FCK value will be directly extracted from this table for 0.05 M values by doing this H lookup equations. So and N value we already calculated, N divided by BH is a 0.1. So for this accordingly this VLOOKUP equation will pick up the value from here, and those are now 0.12. So now this in this equation we know that FYD we know it is 438 megapascal, which is calculated by Fy 500 is a Fy divided by gamma S. So that value we know that 535 megapascal, and B and LR we are knowing that it is 600 mm, and FCK we know that it is a 30 megapascal. Only the unknown value is AS, and in the right hand side we know that it is 0.12. So only simply applying this equation, the unknown value is AS, which is a area of longitudinal reinforcement that we can find out by bringing this known value to the right side to equate this 0.12. Then we are getting area of reinforcement required is 2901 square mm. The same principle we need to apply for tension with bending also. Only thing here change is instead of PU, that PU value we need to consider the net vertical upward load and the correction factor we need to consider the same like as we calculated in compression with bending. And from that we need to refer this chart, the second chart, where this table is derived from that second chart, which is for which is for tension and bending. So this tension and bending values we need to apply. So accordingly the AS FYD divided by BL FCK value is coming 0.13. So substitute this 0.13 with a unknown, one unknown, that is AS is we are getting 3230 square mm, 3230 square mm. So next one is we need to check this calculated reinforcement with the minimum longitudinal reinforcement and maximum longitudinal reinforcement. So for that we already seen this class 9.5.2 and 2 notes. So that page number 164 to be referred for this. So here that equation is given as 0.1 NED divided by FYD, and which is also should be greater than 0.02 AC. So we are applying this equation because all these values are known. We are getting 720 square mm, and the maximum longitudinal reinforcement, it means the calculated reinforcement should not exceed this one. So in case if it is exceeding that, then we need to increase the column sizes. So for that node 3 we need to check. So here that equation is given as 0.04 AC to be considered. That is 4% of the cross section of the column to be considered. So which is coming 14,400, which is greater than this provided or calculated. so hence the reinforcement which is calculated is safe. And here we are going to provide 4 numbers of 20 mm diameter at the corner to each column, and intermediate is 8 numbers. So this will automatically calculated based upon the calculated reinforcement. So this will consider the maximum area of longitudinal reinforcement in both the compression and bending combined with the compression and tension combined with bending, and the diameter which we are using for the corner and the intermediate. So if it is a 16 mm diameter, then it is required 12 numbers of intermediate reinforcement. So 12 plus 14, 4 in corners, it is a 16 number of reinforcement is required. In that 20 mm is 4 at corner and 16 mm diameter as intermediate. So we can provide 20 mm in all intermediate and corner, so that 12 numbers of reinforcement is required. Then the actual reinforcement, if you calculated, which is greater than the calculated or required reinforcement, hence the reinforcement provided is safe, which is 117% of calculated value, which means 17% extra we are providing the reinforcement, hence it is safe. Next, coming to the transverse reinforcement. So for the transverse reinforcement, the explanation is provided in the class 9.5.2 note 1 and 3. So let we see that in page number 164. Here you can see that the transverse reinforcement is provided. So the first case is only the 6 mm need to consider, or 1/4 of the maximum diameter. So maximum diameter is 20. So 20 divided by 4, we will be getting around 5 mm. So 5 mm rod is not available. So 6 mm we can consider. So 6 mm. So both the case it is coming 6 mm only. So we can consider more than that. Maybe we can consider 10 mm as a diameter of the lateral or transverse reinforcement, and the reinforcement spacing also provided here. So the spacing conditions are provided in node 3. So here 20 times the main diameter. So 20 times whichever is the minimum we need to consider. So the 20 times minimum means 20 into 20 mm is a main reinforcement we are providing. Minimum diameter of the reinforcement is 20. So 20 to 20 is 400 mm. And second case is provided as a least or lesser dimension of the column. Least lateral dimension means 600 mm and equal to 400. So only direct away 400 mm. So these are the 4 cases it is given in the class 9.5.2 note 3. However, we are considering the less than this, which is 240 mm as a center to center distance as a transverse reinforcement. So with that, all the reinforcement calculation for column and the column slenderness check and the column dimension and loads are we have seen in this stage. So once after that, we can click this print as PDF. So this Excel calculation is made as a macro version, so that you can directly take this PDF file by clicking that print PDF icon, which is shown in the bottom of this calculation. So now you can see in the right hand side the printed format of this document is visible now. So overview of calculation, which we already discussed in stage 1, and foundation and soil parameters. So loads, all those things we already discussed in that. So check for punching shear, and so all those content and overview of calculation, foundation and soil parameters, loads and load combinations. So stability check here. all are printed now after clicking this print as PDF icon. So here you can see that design of bottom pad which we have seen in the stage 5. So this is punching shear and one-way shear calculation we have seen in stage 6, and this is a final one which the design of column which we have seen in this last stage. So all these are captured in that PDF. So with this design of gantry tower foundation using Eurocode get completed. Thank you. Look description for more related videos. Subscribe to this channel for more updates. Thank you.